Menalaos?
Thank you. So I did this work hand in hand with Dick Hartle and Rosemary Killen. And the point of this work is that we know there's neutrals about the moon, but we've only detected a few species, namely sodium, potassium, argon, helium. You heard about them this morning. And more often in planetary atmospheres, you end up detecting the ions. Ion mass spectrometers being much more sensitive. And we have measured a few more ionic species from the moon than we have their neutral progenitors. We have had wind measurements back in the 90s. We've seen O+. Of course, we haven't seen any neutral oxygen. Silicon plus, aluminum plus. So the question is, given these measurements and the lack of detections of neutrals, can we use the ionic measured levels to constrain the background neutrals? But what complicates the interpretation of the neutral result of the ionic measurements is that there's an additional source of ions straight from the surface when you bombard the regolith with solar wind ions and electrons. So the first question we're trying to answer is, are we primarily measuring the products of photoionization with pickup ions? And in order to answer this, we have produced models of neutrals that we convert to fluxes of ions, and we compare to the surface source from experiments. And if the answer to this question is yes, then it follows that we can answer question 2, that yes, we can constrain exosphere levels for undetected neutral species given these ion measurements. Now, we're certainly looking forward to LAMP results and LADI results, but we're also a little impatient, so I think we have something right now given the ionic levels. So the outline is what I just described. We have 11 species in our neutral model now, and we've converted those with a particle tracing model in ion density and fluxes as would be measured about the moon, and we keep adding species to this. This is just an overview of the different processes that could provide neutrals in this surface boundary atmospheres. And for the purposes of determining the ionic distributions about the moon, there's only 2 classes here that you need to remember. You either have thermal processes or evaporation, neutrals that have low temperature, they've accommodated to the lunar surface temperature, and they're therefore hanging near the surface. Or you have non-thermal processes, UV photons, impacts, or solar wind spattering, and in an increasing degree, as you go from photons to spattering, you launch neutrals that form a corona and that are further and further high up. That single-handedly determines, it turns out, the distributions of the ions of each species around the moon. We rarely get these beautiful coronographic measurements of lunar sodium. More typically, we just get lines of sight into this plane. You sample it at different altitudes from the surface, from the line profile. You just project it to a surface density or intensity at the surface. And this is meant to show that we can match with models of particle transport the measured sodium levels to within a factor of 2. And when we did that in a recent paper last year as a function of lunar phase angle, we found that most likely the sodium content varies by about a factor of 2 per lunation as a result of solar wind enrichment, if you wish, of the grain diffusion in the soil. But for our purposes here, the important news is, the uncertainty in ionic counts, if you wish, that I'll be producing are within a factor of 2. The same point is made here for helium. We've had this helium data going back to Lace in the 70s, and those early models did fairly well, representing at least the enhancement in the night side and the overall levels measured. and Dick Hartle led that work early in the 70s. So I will focus on the next 3 slides on comparing sodium and helium-ion predictions, because those 2 species, we have good models of the neutrals and they're well specified. So the particle tracing is really a solution of Vlasov's equation. Dick submitted a paper that's about to be accepted. And the main assumption is this, that the electric and magnetic fields are spatially uniform, and we're tracing particles in there. And this, among other things, means effectively there's no draping of the interplanetary magnetic field down to the surface. There's no mini magnetospheres or magnetic anomalies, no surface charging, no wave-particle interactions, and ions are still in a ring distribution. And the point is, these are good approximations on the day side, and we're not interested in doing the wake or anything. And there's a lot of low-lying fruit here. Nobody has done. It's a graduate level exercise. This is the simplest, particle tracing problem that you could do, but it will pay off. If you present the trajectories of a large number of ions on a plane perpendicular to the magnetic field, here's the magnetic field's coming out like this, and the electric field's in this way, and so this is a plane tangent to the moon. So you find, for example, for helium, you see almost a perfect cycloid. The ensemble essentially is purely kinetic. And you even see mass conservation there, effectively a dip in density. This is color-coded density in CGS units, logarithmic scale. So you see, where the flux gets higher, you see a dimple in density. It's purely kinetic. And you see this is the size of the moon here. This demonstrates that everything is normalized in units of one ion gyroradius here. For helium plus, the gyroradius is comparable to the lunar radius. And when you do sodium plus here, you see that it's a slightly more different. It's very kinetic still. But here you have an extensive source rate, and you see that you keep adding up to the source rate as you're going downstream. So the sun somewhere here, let's say, this is the drift direction. This is the tail. The main point conveyed here is that the degree of kinetic, everything's kinetic at the moon. But how kinetic exactly it is really a function of the neutral scale height. The difference between this and that, we have thermal or thermally accommodated neutrals in case 1 for helium. We have an extended sodium corona in case 2. These are estimates now with these models of particle density at 100 kilometers altitude on the day side, where this is the direction of the electric field, and this is the direction of the magnetic field, and this was done for 2 IMF configurations, this being the Parker spiral. And basically this shows you the distribution that a lunar orbiter like Kaguya would fly through in terms of density. And in the process of doing this, we also get some very observable densities of several times 10 to the minus 3. It's no wonder they have been observed. This compares what an instrument actually measures. So here's density and here's flux in CGS units for the same IMF configuration. And the rather trivial point is being made here that if you have a 4 pi detector, you actually detect relative abundance. But that proves to be the point of the story, that you really need an omnidirectional flux to make this argument and interpret your spectra. I will not get into this too much. This is really the last point made here, is the ratio of fluxes that you can detect as a function of where your spacecraft flew through. Near the subsolar, there's about the flux of sodium is about twice that of helium. But as you go towards the terminators, there's about 10 times more helium there. So when you see a spectrum, really, you've flown through this, you've integrated for some 30 minutes, it's some mix of this. But it's no wonder that this is approximately what Kakuya reports, some value almost 1-to-1 between sodium plus and helium plus. Now, the point of the exercise is to get to this, to extrapolate to other lunar neutrals, and I've produced a model with 10 of them, and I had a poster on this, and we used this to produce some estimates for Ladi. What we did is, of course, take this model now and produce the resulting ions. One comparison is for ions from the non-thermoneutrals. Here's aluminum plus on one side and sodium plus. The difference on the left is this was produced with a uniform neutral source, such as impact vaporization, whereas this has a solar zenith angle dependent source from photons. And you see effectively no difference in this pattern. And so we can't attribute really a solar zenith angle dependence in measured ion counts to a non-uniform exosphere. This is really what Kakuya is measuring, but it's not an exospheric effect. It's not exo-ions that you're seeing. Ions from thermoneutrals. So this point demonstrates that if the neutrals all have the same temperature, if you wish, then you go from more of a fluid interaction like H2 plus, which is as fluid as you'll get at the moon, to carbon plus and then sulfur plus. You see it's highly kinetic. It peaks very sharply at some point in the direction of the electric field. This is the suite of different distributions that we can get with these models, and the answer is if we had a very sensitive instrument, we'll be able to tell neutral distribution or temperature based on these detections. But rather the important point is this, which is we've had these estimates of secondary ions from lunar solar simulants being bombarded by solar wind ions, and you see you expect about 10 to the 3 fluxes of ions of 10 to the 3 per square centimeters and seconds coming off the surface from Reykjavik's early experiments. This, for the first time, we have an estimate of the exo-ion flux at, say, 100 kilometers altitude. What is immediately obvious is that species like aluminum, silicon, sodium is more than enough in the exosphere to overwhelm your surface source rate. For other things like calcium, magnesium, and iron, it's really the surface source that dominates. Finally, if these are the two sources of ions in the lunar environment, what do we find by comparing this with measurements? Well, the big issue that stands out right away is where is all that O plus that everybody's reporting coming off? If you do the numbers, it turns out you either need about 10 times as many oxygen neutrals, or you need an ionization rate that's about 10 times more efficient than photoionization. So we're investigating this issue. I mean, there's too much O plus being measured is the point of this. We can account for this with what we expect to be there in the exosphere. The second major point is we had a putative detection of H2 plus now from the Chinese Chang mission coming out this week in GRL. You see that we use for H2 plus the upper levels from the Stern paper there. And you see that their detection corresponds to about 110 to 100 times less than that. So this is a clear first indication that yes, we can constrain the underlying neutrals by looking at ions. 2 points being made here, that both surface and exospheric ions contribute to the surface environment to different degrees depending on species. The exo-ions that can be attributed to the exosphere, in other words, are very observable in many cases. And we can use relative ion abundances to constrain levels of undetected neutrals.